couple of very simple rules that I should repeat every day about the use of Zoom, of the platform for our Congress. Please leave your microphone, hold your microphone switched off during the whole talk, because it would be difficult for me to identify the person with an open microphone, and should be a little bit uneasy to mute everybody. Second thing, we will have a space for question and answer immediately after the talk. You're supposed, please, to type to me privately in the chat that you want to make a question. Okay, just write down question or Q, and I will follow the order of who's going to write me, who wants to make questions. Okay, this is about the simple rules. We will have a second talk after the first one. So in 2 hours, the second talk will be in Spanish from Professor Eleonora Orlando from Buenos Aires, University of Buenos Aires. I want to announce today, I want also to announce today that tomorrow at 1 o'clock in Costa Rica, we will have more or less half an hour time to give a feedback to Professor Katarzyna Jachut about the talk she gave on Monday, because as many of you know, we had problem of connection on Monday, and Professor Jachut couldn't receive properly the questions. Everybody will receive a paper, an email message with the paper of Professor Jachut. You have to remember the topics and the main points, and take part in the feedback tomorrow at 1 o'clock. So everybody's invited to be present. After the first introduction to the day and the first recommendations, I pass to introduce our first guest, Professor Gillian Russell. Gillian Russell is a professor of philosophy at the Dianoia Institute of Philosophy at the Australian Catholic University in Melbourne, and a part-time professor at the Arche Research Centre at the University of St Andrews. Before moving to teach in Australia, she was alumni distinguished professor in philosophy at the University of North Carolina at Chapel Hill. And from 2004 to 2015, she worked at Washington University in St. Louis. She was an undergraduate at the University of St. Andrews and did her PhD in philosophy at Princeton University in 2004. In 2005, she was CILEM postdoc at the University of Alberta in Edmonton. Gillian Russell published in 2008 the very influential book on the analytic synthetic distinction, Truth in Virtue of Meaning, a defense of the analytic synthetic distinction, for the Oxford University Press. Furthermore, she wrote several articles on the philosophy of logic, epistemology of logic, normativity of logic, indexicals, logical pluralism, and logical nihilism. She's currently working on the issue of barriers to involvement. That is, the thesis of the impossibility of obtaining certain types of conclusions from certain types of premises, such as duty from being, statements about the future to starting from statements about the past. It is precisely in the frame of this last thematics that Professor Russell will give her talk today, with the title Hume's Law and Ought Implies Can. Thank you very much, Professor Russell. I give you the word.
Thank you, Lorenzo, for that very generous introduction. Buenos dias, everyone. That's now 2 of the 5 words I have in Spanish. So I'm afraid I will have to proceed in English. So as you were just hearing, this is going to be a talk about Hume's law, the thesis that you can't get, using logic, normative claims from descriptive claims. So it's in part a talk in logic, but it's not only logic, or at least I think it's not only of interest to logicians, because the issue of whether or not you can derive normative claims is of interest to like lots of different people in philosophy. So given that, and given that I think many of the big ideas in this talk can be understood without like very fine detailed grip on some of the technical details, where it's possible to present them in an intuitive way, that's what I'm going to be doing. Sometimes there will have to be some definitions and some proofs, but I'm trying to make the talk as easy to access for anybody who might find it interesting as possible. But given that I'm doing that, there is a different danger, which is that some people might hear some of the intuitive stuff and think, well, what do you mean by that? There are a couple of different specifications, like we saying things up this way or this way. And those people might find it helpful to have access to a document that has more of the technical details. So what I've done is I've emailed the organizers a handout, which is different from the slides and has a few more like proofs and definitions and goes into a few more details. You don't need that to understand the talk, I think. I'm going to share some slides. I think that's all you really need to follow the talk. But if you do get interested in some particular detail, feel free to take a look at the handout as well. Okay, so let me see if I can share these slides. Share screen. Go. Okay, so I hope it's now the case that people can see the slides. Is that right?
It's perfect, Gillian. Thank you very much.
Thank you. Okay, so Hume's law and ought implies can. I'm going to start with the quote from Hume that everybody uses when they introduce this topic. So here's why we're calling it Hume's law. And I'm going to have to, I think, move some of these windows so that I can read this. Okay. In every system of morality, which I have hitherto met with, I have always remarked that the author proceeds for some time in the ordinary way of reasoning and establishes the being of a god, or makes some observations concerning human affairs, when of a sudden I'm surprised to find that instead of the usual copulations of propositions, is and is not, I meet with no proposition that is not connected with an ought, or an ought not. This change is imperceptible, but is, however, of the last consequence. For as this ought or ought not expresses some new relation or affirmation, it is necessary that it should be observed and explained, and at the same time that a reason should be given for what seems altogether inconceivable, how this new relation can be a deduction from others which are entirely different from it. Okay, so given that passage, people often refer to the principle that I'm going to be talking about as Hume's law. But really, what I'm doing here is not Hume interpretation. And there is a thriving industry of interpreting Hume on this particular subject, some of which might mesh with some of what I'm going to say, some of which won't. But I think even given that there's this passage from Hume, there's a really intuitive idea here that I think a lot of people find very plausible, regardless of whether it turns out that that's what Hume meant. So here are a few other attempts to say what it is. So sometimes people say you can't get an ought from an is. Sometimes people say you can't get normative claims from descriptive ones. Sometimes they say valuative instead and factive on the other side. Sometimes they talk about the autonomy of ethics. And sometimes they say no set of purely descriptive sentences entails a normative sentence. So I take it there is kind of an intuitive idea here, but it's not completely obvious what the right formulation of it is. Okay, despite that, Hume's law, maybe because of that, Hume's law is deeply controversial in philosophy. So there have been many attempted counterexamples and defenses. For example, it has been endorsed or defended in some form by Hume, Popper, Hare, Nell, Smith, Anscombe, Shorter, Thompson and Thompson, Flew, Jackson, Jagger, von Kutschera in German, Carmo, Pigden, Schertz, Guevara, Singer, Brown, and Fine. That's, you know, a summary of some of them. It's not all of them, but then rejected in some form by Reinen, Foote, Anscombe, Pryor, Black, Searle, Mavrodis, Kurtzman, Geach, McIntyre, Nelson, and Mason. I have no plans to go through the entire controversy involving all these things. I'm going to try to focus on one particular issue, but as you'll see, Hume's law has even generated a certain amount of intra-philosopher controversy. So here's a famous quote from A.N. Pryor. It's often been said, in fact, I've said it quite emphatically myself, that it's impossible to deduce ethical conclusions from non-ethical premises. This now seems to me to be a mistake. Okay, so it's really common when somebody talks about this topic in logic that they focus on one particular counterexample that's often associated with A.N. Pryor from his paper, The Autonomy of Ethics, Logic and the Autonomy of Ethics. And this is the counterexample. So imagine that D is a schematic letter that can only be replaced with descriptive sentences, and N can only be replaced with normative sentences. So your premise is some descriptive sentence D, and then by disjunction introduction, that entails D or N. Okay, that's the start of the counterexample. Second part kind of anticipates a response where somebody says, yeah, you know, that conclusion, D or N, I'm not really sure that that's a normative conclusion. And if it's not, this wouldn't count as a counterexample. Because in order to have a counterexample, we need descriptive premises, normative conclusion, valid argument, right? So then Pryor says, fine, suppose that it's not normative. Then take it as a premise in the following argument. D or N, not D, therefore N by disjunctive syllogism. Okay, so huge literature on that. It's not what I'm going to focus on today. Today I want to focus on a different attempted counterexample to Hume's law. This one is important because it involves the interaction between kind of two different domains, not just the normative, but also the modal. And so it seems to require a complex logic, one that has, say, both modal operators and deontic operators, in order for you to study it properly. And so you might, say, prove a version of Hume's law about a very simple deontic logic, but if it doesn't have any modal operators in it, you haven't said anything yet about counterexamples like this one. So this is like a sort of more advanced counterexample in a way that I'm especially interested in solving. So it's going to be my main focus. Okay, I've heard this counterexample from various different places. I've heard it asked as part of questions at talks. So I know that it's kind of in the air, but I found one place where it's written down fairly succinctly and relatively early on. So Mavrodis in Analysis in 1964 wrote, many ethical philosophers appear to accept the view that ought implies can. This view, which seems quite plausible, can perhaps be formulated more precisely as 1. Statements of the form N ought to do X entail the corresponding statements of the form N can or is able to do X. But 1 is equivalent to 2. Statements of the form N cannot is unable to do X entail the corresponding statements of the form it is not the case that N ought to do X, and 2 appears to say that there is a non-normative statement which entails a normative one. It's perhaps characteristic of the state of the debate that I read this entire argument in one paragraph in Analysis and was like, thank goodness somebody said this in a short form. I think we can make it even more concise if we avail ourselves of the resources of modal deontic logic. So ought implies can, right? And I'm just using P here, maybe a more general version of this ought to have like phi or a metalinguistic variable in there, but let's just stick with the sentence letter P. If it ought to be the case that P, well, then it follows that it's possible that P, I think one of the ways people intuitively get themselves into thinking why this is the case, they're thinking, well, when you're trying to figure out what you ought to do, right? Look at all the things you can do and figure out which ones are the best, right? And then, anything that takes place in like all of those best scenarios, well, that's what you ought to do, right? So, if it's something that you ought to do, you better be able to do it. Right? Okay, so we start with that principle and then we contrapose it. That gives us, it's not possible that P entails, it's not the case that it ought to be the case that P by contraposition. And this line is our potential counterexample. So here's exactly why. The premise looks non-normative. It's certainly not the kind of thing we had in mind when we're talking about normative claims. Like, it's not the case that it's possible that P is not a classic example of a normative sentence. The conclusion looks normative, at least in the following sense. It's got a big ought operator in it, and that suggests that it's going to be normative. And since, on the assumption that the argument is valid, we appear to have a counterexample. So suppose you're interested in defending Hume's law against this counterexample, and that's my project. I'm interested in that. What are your options? Like, how could you go about this? Well, here are 4 things you might say. So I've put the counterexample back up there. First, you might say that contrary to appearances, not possibly P is really normative. Now, you'll have to come up with some story about why that's the case, but if you could find a reason to say that, then you wouldn't have a counterexample anymore. Secondly, we could say not ought P is not really normative, right? And you can imagine somebody saying, well, look, I know that ought P is normative, but is the negation of ought P normative? Like, is the class of normative sentences closed under negation? That's kind of like an interesting question. Maybe that's somewhere we could put some pressure. Third option, you could say that the argument isn't valid. This is the kind of tack that's taken by Charles Pigden in his defense of Hume's law. Pigden thinks that Hume's law is an instance of a more general principle, the conservativeness of logic, which means that roughly if you have expressions which are not logical expressions in the premises, so if you're in the conclusion, then they have to have been in the premises. There's a question there where you say, well, what about the logical normative operators? What about ought and possibly? And Pigden says that's not logic. There are no deontic operators. There's no logic of normativity. And in fact, same thing for modal logic, same thing for tense logic. And we end up taking kind of a Quinean line where first order logic is really all you get. So the quantifiers are as far as you go with the logical constants. If you're kind of excited by the chance to use these richer resources in logic, you probably won't like that particular response. But also, I'm tempted to think that whatever the conception of validity or logical consequences that's involved in Hume's law and this kind of intuitive thought that you can't get normative claims from descriptive claims, it's probably not this like highly specialized, restricted version of logic where only first order logic turns out to be logic. Okay, last option. We could restrict the barrier in some way so that it doesn't conflict with this, this principle, this argument. So we could say, look, you can't get normative claims from descriptive claims unless the following condition is met. So there'd be like a limitation on the barrier, wouldn't be as strong as we thought it was. But now there's the question, well, what are those restrictions going to look like? And are we in danger of having a barrier that's too ad hoc, that was just like changed in response to a particular problem? Okay, I want to say a little bit about option 2, because I think it turns out to be much less promising than it might have seemed. And in fact, I think it's basically a non-starter. So option 2 was to say that not ought P isn't really normative. The relevant observation here is that ought implies can, and its contrapositive are only 2 of a larger class of interrelated deontic modal principles. And it seems really likely that they're going to stand or fall together. So let me tell you about some other principles. So here's our first two, ought implies can. Then you contrapose to get deontic modal 2. And then if we substitute not phi for phi, and then use box instead of not, diamond, not, and permissible instead of not, ought, not, we get this, dm3. And if we contrapose that, we get this. And here's another principle that you might think you can get to from the same sort of intuitive reasoning that would get you ought implies can, which is something like if something's permissible, then it's possible as well. So kind of you're selecting, what you ought to do by looking at certain possible worlds. And you may as well only look at the possible worlds where you're able to do those things. They're really possible. And so if something's going to turn out to be permissible, it's going to turn out to be possible. And if we like that, which strictly speaking, I think is slightly stronger than DM1, then we can go through the same process again. We can contrapose it, we can substitute in some negations, and we can end up with this list of 8 different principles linking the modal and the deontic notions. And really, the strongest counterexamples to Hume's law are going to be DM3, which is in red, and DM7. So in both these cases, there's no negation floating around to be talked about. So although option 2 might have seemed promising in the case of DM2, we have other principles that are closely related to DM2 where that's not going to help. Okay. All right. So here's a thought. Maybe we could introduce a particular logic and use that to help us think about this situation. There are going to be 2 places in this talk where I introduce particular logics. They're mostly for the purposes of illustration and to give us clear examples of things. And so given that, I have made these logics as simple as I possibly can, given the use that I need to make of them. So this may not look simple to everybody, but I will illustrate it in a minute that I hope will, in a way that I hope will make it a bit simpler. So one of our models is going to be a quadruple. You have to have a set W, which is a non-empty set of points. You can think of those intuitively as the set of possible worlds. You'll notice that there's no accessibility relation here. So if you're used to thinking about modal models, just assume that that relation is universal. And then S is a non-empty subset of W. And I'm calling this the set of superb worlds, but you can think of them as the set of worlds that conform to the normative standards, that they've reached the standard to be good worlds. They're kind of the normative heaven of the model. It has to be non-empty, but that's the only restriction otherwise, as long as it's a subset of W. And then one of the worlds is designated as the actual world, so that's one of the elements of W. And then we have an interpretation function that maps sentence letters and worlds to 1 and 0, representing the true and the false. Okay, here's an example. It's like a picture of a model that would fit this definition. So we got to have a set of possible worlds, and in this diagram of the model, you can see that there are 5 possible worlds: W1, W2, W3, W4, and then in the middle, there's this square possible world. That's the actual world. So the square is supposed to represent that this one is the actual world in this model. The gray area is the set S. So in this model, S is the set containing W1 and W2. And so this is the sad fact about this model. The actual world is not one of the worlds that meets the normative standards. And then finally, we have the interpretation function. And the interpretation function is supposed to tell us the truth values of sentence letters relative to worlds. And so we've shown this in the diagram by, if a sentence letter is true relative to a world, then just under it, you'll see that sentence letter. So R is true at the actual world. But if the sentence is false, I've written not, and then that sentence letter. I think there are at least some people in the audience that will think that's a little bit sloppy. Yeah, maybe it is. I should maybe have written 1 and 0 under the sentence letters and not kind of confused saying that something's false with saying that the negation is true. But this is what we have for now. So at the actual world, P is false, Q is false, and R is true. Let's see. Okay, so this is the same model again. I just wanted to keep it on the screen while we say some things about it. So the truth conditions for the possibility operator, the diamond, possibly phi is going to be true at a world just in case there's some world in W where phi is true. So if we're interested in whether possibly P is true at the actual world, we've got to see whether there's any world in W where P is true. And I see, oh yeah, W3, P is true. And so diamond P is true at the actual world. As you'd expect, box phi is true at a world just in case phi is true at all the worlds. So box phi is going to be false at the actual world because, for example, it's not true at the actual world itself, but it's also not true at W4. And then we have our two deontic operators as well. So we've got possibly phi. Possibly phi will be true just in case there's some world in S where phi is the case. So, sorry, it's permissible that phi, I might have said possibly. Okay, it's permissible that phi will be true at the actual world just in case there's some world in S where phi is true. So it's permissible that P is true in the actual world. And it's permissible that Q is also true in the actual world because there's this world, W2, in the set of superb worlds where Q is true. And then finally, ought phi is going to be true at a world just in case at every superb world phi is true. And so it ought to be the case that P, that is true at the actual world in this model because P is true at every superb world, W1 and W2. Okay, so that's a brief introduction to the truth conditions for our modal and deontic operators. And now, just got some catching up to do to make sure we get a consequence relation. So truth in the model is truth at the model's actual world. So if you want to know if ought P is true in this model, you have to ask whether ought P is true at the actual world. And it is, so ought P is true in this model. You can also see that not necessarily P, that's true in this model because we look at W4 and P is false. Not ought Q, that's true in the model because Q is false at W1, which is a superb world. And then if you've got something like P or possibly Q, right, in order for that to be true at the actual world, we either need P to be true at the actual world or, and it's not, permissible Q to be true at the actual world, but that's true at W2. And so that disjunction is true in the model as well. And then we use this notion of truth in a model to define our relation of logical consequence. So gamma entails phi if and only if every model that makes gamma true makes phi true. So in the way it's sometimes put, these are pointed models. And our notion of logical consequence quantifies over like truth in a model. Okay, one thing we can say about this model is it gives us a counterexample to the claim that it ought to be the case that P entails P, because in this model, ought P is true, but P is false because P is false at the actual world. But it turns out that each of our DM principles, so including ought entails can, hold in this logic, and the handout has some sample proofs of that fact. Okay, so we've set up this deontic modal logic that's going to enable us to maybe give some clearer examples and think more about how to prove Hume's law, but it doesn't yet tell us which of those four options is like the best one to go for. Right? Are we going to try and say the conclusion isn't normative? Are we going to try and say the premises aren't descriptive? Is it not valid? Or do we try to limit the law in some way? And part of my shtick in thinking about Hume's law is to see Hume's law as just one of a small collection of barriers to entailment that are of interest to philosophers. So let me give you some examples of some more. You can't get universal claims from particular ones. So this was something that comes up a lot in, say, discussions of logical atomism. Russell says you know, no matter how many particular claims you gather together, that won't be enough to establish a universal claim. In order to get that, you have to have a universal claim in your premises. Right? So there seems to be something like a particular general barrier, the same way there's a descriptive normative barrier. You can't get claims about the future from claims about the past. So this is also something that we associate with Hume, especially thinking about the problem of induction. You know, if we could deduce claims about the future from the data we've gathered from the past, that would be really nice. We would be able to like establish stuff about the future. But this sort of so apparently obvious a point that you can't deduce claims about the future from claims about the past, that it's like a standard undergraduate misunderstanding of Hume on induction, that the only problem is that you can't deduce claims about the future from claims about the past. You can't get claims that say how things must be from claims that say only how things are. So if I like do some investigating and I find out that say all renates are chordates, it doesn't follow from say the data I've collected, you know, the fact that all renates are chordates in the actual world, that all renates have to be chordates, that in every possible world, all renates are chordates. So it doesn't follow necessarily all renates are chordates. You can't get indexical sentences from non-indexical ones. So this is something that I associate in its earliest form with Castaneda, but you also find versions of this in John Perry's work, where he talks about the messy shopper, and Rudolf Lingen's in the library, and the essentiality of the indexical. Like, you know, this could clearly be seen as like related to the fact you can't just deduce indexical claims from the descriptive claims that you have. And also David Lewis talks about this a bit, and there's this famous thought experiment with two gods who know all the non-indexical truths, and there's a question about whether they can deduce the indexical ones. And it seems clear that the answer is supposed to be, yeah, kind of not. Okay, and then finally, you can't get an ought from an is. And one thought that I have certainly had is that while Hume's law, the last one, is extremely controversial, the other four are not, and are often thought to be, you know, some form basically correct. There might be some questions about exactly how we formulate them, but certainly there was something right about the thought that you can't get universal claims from particular claims. And so you might think, if we could establish a single way to argue for or prove claims of this kind, well then they would each kind of benefit from this unified explanation of what is going on and support each other. And so in particular, the uncontroversial ones would provide some support for the controversial one. So here's a question. Is there anything like the ought implies can style of counterexample to any of the other barriers? So here's one thought. Just as you might think that ought implies can, so you might think that will implies can. That is, only possible stuff can happen in the future. If in the future phi, then it's possible that phi. Okay, this is not the only sense of possible. So let me just put this clarifying point in. There's also a sense of possible that is time relative, so that what is possible can change over time. And that allows us to say things like, he needs to pass intro chemistry this semester so that he can take physical chemistry in the spring. And the thought is that he can't take it yet, but when he's passed intro chemistry, then he'll be able to take it. Or interstellar travel isn't possible now, but it could be in the future. Right? That suggests that what's possible can vary over time. But we also have an absolute sense of possible in which only possible things can happen. And this allows us to say things like this. There won't be faster than light travel in the future because it isn't possible. Or he isn't going to pass intro chemistry because he can't. Even with 100% on the final, he still wouldn't pass. Okay, so there's one sense of can on which will implies can. And now we can make Mavroda's move from the Hume's law debate if will implies can, we can contrapose to get can't implies won't, which is a putative counterexample to the past future barrier. So here we've contraposed it. Stuff on the left, not about the future. Stuff on the right seems to be about the future, but valid argument. Okay, and again, we find a similar range of corollaries. So here's one. So the G operator is from tense logic. It means that every time in the future, phi is the case. And if that's so, then phi has to be possible. We can contrapose that. If it's not possible that phi, then it's not the case that every time in the future phi. And then we can substitute in not phi for phi and like define our operators around, and we get if necessarily phi. Well, that entails at some time in the future phi. And we get a few more by doing similar kinds of thing. And again, TM3 and TM7 seem like the cleanest, strongest counterexamples. So on the left-hand side, we've got something that doesn't seem to be about the future. And on the right-hand side, we've got something that clearly does seem to be about the future. Okay. Okay, it's time for another logic. At this point, it will be useful to have a specific tense modal logic. So we're going to introduce one. Again, the key definitions are on the handout for anyone who would like to check the details. I'm interested in keeping this as simple as possible and developing it in a way that will give us the TM principles so that we can work around that argument. Okay, so this time our models are going to be 5 tuples consisting of a non-empty set W, which is the set of possible world, a non-empty set T. In fact, T is going to be the set of integers. Just think of it that way. They have their own ordering, of course. And we will think of that informally as the set of times. You can do this in different ways, right? So we could have the set of reals there, or we could just have a set of points and introduce an additional ordering relation on those points. Of course, we could have an accessibility relation to the possible world as well, but we're trying to keep things very, very simple and not introduce anything that would just be distracting. So we've got sets of worlds and sets of integers, a set of integers. And within those, one of the elements of W is the actual world. And one of the elements of T is the now. So the present moment, if you like. And then finally, we have an interpretation function. And the interpretation function assigns truth values to sentence letters relative to pairs of times and worlds. So this grid is kind of a diagram of one of these models, a very simple one. We've only got 5 times here, T1, T2, and T3, T4. I'm imagining that time goes up the page. So the past is at the bottom, the future is at the top. And we only have 3 possible worlds, W, U, and the actual world in the middle. So we got a W, we got a T, we've got the actual world and the now marked out. And then the interpretation function has to tell us for each time world pair what sentence letters get, what truth values there. And this time I've, inconsistently, I guess, just left out the sentence letters of P, Q, and R if they're not true at that time and world, and written them in if they are true there. So for example, at T3W, right, at time T3 and the world W, P and Q are both true. Okay, this shaded area in this model doesn't correspond to anything in that 5 tuple in the definition of a model, but you can think of it as the future in the actual world, right? So it marks out, relative to the actual world, every time that comes after the now, right? And so it tells you what the actual future looks like. So for example, at T3, P and Q will be true, but R will be false. And then at T4, P, Q, and R will all be true. Okay, so I hope that helps you read those tables a little bit. Okay, yeah, so there's some information here about it. The table shows the I function. Add is the actual world, N is the present moment, the now. Okay, so how do we read some of these operators on these kinds of models? So the tense ones are pretty intuitive. So future phi will be true at a time T and world W, just in case in that world, there's a later time where phi is true. Okay, so if I'm looking at, say, T2W, and I want to know if future R is true, then I stay in that column in that world, and I look and see if there's a later time where R is true, and there is, there's N, right? So R is true there, and so future R is true at T2W. And then G is just the universalized version of that. So G phi is true of the world and the time, just in case for every future time in that world, phi comes out true. A little bit trickier to think about are the modal operators. We want them to get this like absolute interpretation, so that if it's possible at all, like if it's possible at any time or world, then it's going to count as possible absolutely full stop. It doesn't change over time. So possibly phi will be true relative to T and W if and only if there's some world and time in the model that makes phi true. Okay, so if any one of these boxes has R in it, that will make possibly R true at all the rest. And then similarly for box phi, right? So that will be true just in case at every time and world phi comes out true. Okay, so if you can see the way the model's been set up here, P is true in every single cell of this table, right? So that's what's required for box P to be true. And so this is a model in which box P comes out true. Okay, so box phi turns out to be a rather strong claim. It requires that phi is true throughout the set of world slices in T times W at all cells in the table. Okay, and then just getting our bookkeeping out of the way, a sentence is true in the model if it's true at the now actual world of the model. So if it's true in that middle cell, and gamma entails phi, just in case all models that make every member of gamma true make phi true as well. Okay, this logic validates all the TM principles. There are a couple of sample proofs on the handout. Okay, let's see if we can use the logic to formulate a past-future barrier. In order to do that, we need an idea of what it is for a sentence to be about the future or about the past. Okay, so here is kind of a key informal idea that we're going to have to do some work to make more precise. So here's the vague idea. Sentences are really about the future if their truth value is somehow sensitive to changes to the future. We're going to look at two things you might mean by changes to the future and two things you might mean by sensitive to. And we're going to look at some of the consequences of like the different specifications. And in some ways, like there's a lot of detail in the next section just coming up, but it's going to be summarized in a table at the end. So if you find yourself tuning out some of the details, there's a summary slide coming up, which will remind you of where we got. Okay, so here's the first way of thinking about changing the future. See that gray box that represents the actual future in the left-hand table here, right? You are allowed to change any of those sentence letters. So erase the whole thing and put in whatever sentence letters you like. So for example, in the model on the right, we've done that. We've erased all the ones at and T4, and we've written in Q and R at and T3 instead of P and Q, right? That counts as unrestricted future switching, right? You're only allowed to change stuff in the future of the actual world, but you can make any changes you like to the I function. Okay. One thing to maybe think about this is if we're thinking about sentences that are really about the future, being sentences that are kind of sensitive to changes in what goes on in the future, this is going to make box P future, right? Because in the right-hand model, box P isn't true anymore, right? There are cells where P doesn't hold, right? And so this is making box P sensitive to changes in the future. Okay, so interesting consequence. All right, different kind of future switching, restricted future switching. This time you swap the actual future with one of the merely possible ones. So this restricts the changes to the actual future to things that were already possible in the model. If you like, you only get to choose from among the possible futures. So what's happened between the left-hand and right-hand table here is that the actual future in the left-hand model has been moved over one cell to the right. So it's now the actual future, or it's now the future for you. And the future for you has been moved into the gray square. So instead of saying PP right under you, it says PP right under the actual world. So we've swapped the futures from this possible future in you and made that the actual future. That's restricted future switching. And of course, that has the consequence that if box P was true in the model, this isn't going to change that. If box P was true in the model, P had to be true in every cell. And so moving some cells over from a different column is not going to change the fact that that holds. Okay, so quick thing about the key differences. Box P and diamond P can change their truth values with unrestricted future switching, but not with the restricted variety. Okay, second kind of precisification is, what do I mean by being sensitive to changes in the future? Like, it's something to do with changing your truth value, but there are a couple of different things you can mean. And in this slide, I've used this symbol in LaTeX, it's curly V. It's like a sort of curly shaped V, so it says that fragile. I'm using that to mean future switching. So curly V fragile is like fragile with respect to the relation of future switching. I'm using it because it's like things change once you get into the future, and there are two possible ways to go. Okay, so a sentence phi is future switch fragile, just in case for all TM models M. If VM phi equals 1, there's at least one model N such that N is a future switch of M and Vn of phi equals 0. The key thought here that can be a little bit hard to get your head around is what's needed is whenever the sentence is true in a model, you can always make it false by future switching. One case where that's going to be like interesting is cases where you have disjunctions of future and non-future things. So if you have P or future Q, and you ask, is it the case that whenever this is true in a model, you can make it false by future switching? The answer is actually no. But sometimes when it's true in a model, you can make it false by future switching. Okay, so the problem is it depends how it's made true in the model. If the disjunction is made true by making P true, then changing the future is not going to make any difference. It's just going to stay true. But if P is false and you make the disjunction true by making FQ true, then changing the future can change the truth value of FQ. And since P wasn't true, you make it go false. Okay, so that's fragility. Here's maybe a slightly more intuitive way of thinking about future switch sensitivity. A sentence might be future switch breakable. So a sentence phi is future just in case, so this should be, I guess, future switch breakable, just in case there are TM models M and N such that one's a future switch of the other, and one makes it true and the other makes it false. Okay, so you can take the sentence from true to false by future switching, but it's not requiring that that's always possible. We just got to be able to come up with some model which is such that if you change the future, it changes the truth value of this sentence. Okay, so a remarkable thing about that, as I noticed, disjunctions of P or FQ are both restricted and unrestricted future switch breakable. And there's the explanation again of why. FP will be future on both the unrestricted and restricted conceptions of future switching. And box P will end up being future given unrestricted future switching, but not future on the restricted conception. Okay, there's one more crucial point about these 4 options that you get from the 2 different disambiguations of changing the future and sensitive to changes in the future. And it is that if you go with future switch fragility instead of future switch breakability, it's really easy to prove Hume's law. So fragility makes it easy to prove barriers, breakability does not. just to show you how this goes quickly, suppose we define the sentences in our premise class here, the past, as those which do not have their truth values changed by future switching. And if we have a definition like that, well then we can prove that no set of sentences that is past entails a sentence that is future switch fragile. I think actually maybe that should say no satisfiable set of sentences that is past entails a sentence that is future switch fragile, but moving on. I mean, the idea is, suppose you've got a model of gamma, right? Either that makes phi true or it doesn't. If it doesn't, you got a counterexample. If it does, then do some future switching. And given that gamma is future switch fragile, there's always going to be a way to make it go false. So then you get this model in which it's false, but gamma's still got to be true there because it was future switch stable as it was. And so there's your counterexample. Okay, but this proof will not go through with future switch breakability in place of future switch fragile, since the crucial move that there must be one doesn't hold. Breakability requires only that there is sometimes a future switch that makes phi false, not that there is always one. Okay, so here's the summing up what went on in that kind of detailed section slide. So it tells you a little bit about how we end up taxonomizing things. And I'm just gonna say, I guess I think so, that option D gives us the most intuitive taxonomy, right? So FP comes out as future. I think C is just like intolerable, right? To have FP come out as not future, it's just a disaster. The disjunction P or FP that comes out as future, I find that fairly plausible, but box P comes out as not future. I didn't talk a lot about this, but on options D and B, you also get a dichotomy in the sense that you've partitioned a set of sentences into the ones that are future and the ones that are not. Whereas with fragility, you tend to get, there's the past sentences, the stuff that's neither, and then there's the future sentences. Okay, so there's one problem with option D, and that's that it isn't obvious how to prove the barriers of breakability rather than fragility. But maybe that's actually a positive if we're interested in a limited version of the barrier. I mean, if we could already prove that you can't get any future stuff from past stuff, we wouldn't have any options to like say except in the following cases. Okay, so I'm going to take a step back again and ask, okay, so that's the normative barrier and the future barrier. Do we get any of these like complex logic issues with any of the other barriers? And I think we do. And I think this one is really useful for thinking about what the right answer is. So the I on the right-hand side of this entailment claim is the first person pronoun I, it's the indexical I. And I'm not going to set out a full indexical logic, but this argument is valid in Kaplan's LD. And it says, look, if everything is Q, then I am Q. Okay. And one way of thinking about why that's valid is, well, look, we think of, one way to think about the indexical sentences, there are sentences whose truth value can change when we change the context of use. Right? So if somebody else utters the sentence, then somebody else is going to be the referent of I. Right? So if you have all these different individuals and some of them are Q and some of them are not, then changing the context so that somebody else is the agent of that context is going to make the sentence go true, go false, go true. So indexical sentences are vulnerable to context shifts. Right? And so you might think, well, that means there's going to be a barrier between sentences that are not vulnerable to context shifts and indexical sentences. You can just like shift the context and make it go false, and then you get a counterexample. Right? But actually, after you think about that, you think, no, it's not always going to work. There are some premises that are such that if they're true in a model, it shuts down the difference that context shifting can make. So for example, if all the individuals are Q, you won't be able to shift the context in such a way that you get a speaker who's not Q. Okay. All right. So in this indexical case, we of course have the usual 4 options, right? So non-indexical sentence on the left, indexical sentence on the right seems to be valid. We could say that, you know, IMQ is, gosh, that's a terrible example, isn't it? I hadn't even thought of the connotations. Okay, QI is not indexical. I think that's a non-starter. You could say for all x, Q of x is indexical. Yeah, okay, so it's pretty standard to think that natural language quantifiers are at least context sensitive, but like formal quantifiers don't have to be. And in fact, we've set this one up so that it's not. And so this is going to be non-indexical. You could say the argument isn't valid. I think that's deeply implausible. This is just, universal elimination, that should be. Or you could restrict the barrier in some way. So here's kind of the justifying thought I was just running through. Indexical sentences are sentences whose truth value is breakable with context shifts. Constant sentences are stable with context shifts. So if you have an argument from the stable constant sentence to the indexical one, you'd expect to be able to generate counterexamples by finding a model in which C is true and then varying the context until I goes false. So you would expect there to be a barrier, except there's this one situation where it won't work. If making C true has restricted the model so that no contexts are available that would make I false, for example, all context shifts of models that make C true make I true, then it won't happen. Okay, so this suggests a formulation of the restriction. If gamma is non-indexical and phi is indexical, gamma does not entail phi unless every context shift of any model that makes gamma true also makes phi true. So this is a restricted version of the barrier. It says gamma doesn't entail phi unless some condition is met. And in general, the stronger that condition is, the stronger the barrier will be. So imagine if I said, I'm not going to the party unless Katie goes too, right? Or if I said, I'm not going to the party unless hell freezes over, right? That second condition is stronger and it expresses like a bigger barrier to me going, right? So the stronger that unless clause is, the stronger the barrier is in general. Okay, there's a proof. I won't run through it right now because I'm worried that I'm running out of time, but we can prove that. And then we can use exactly the same solution in the tense modal case as well. So we can say that a sentence is future if it is restricted future switch breakable. And then we say a sentence is past if it's basically not restricted future switch breakable, that is restricted future switches don't change its truth value. And then we can express the past future barrier theorem. If gamma is past and phi is future, gamma doesn't entail phi unless every future switch of any model that makes gamma true also makes phi true. So what does that tell us about the counterexample from box P to FP? Well, first of all, box P is future switch stable, so it's past. FP is future switch breakable, so it's future. But any model of box P is such that all restricted future switches of that model make FP true. So the argument is valid, but it meets the theorem's unless clause. So we've basically restricted or limited the barrier so that this is no longer a counterexample. Okay. The argument would have been a counterexample to a completely unlimited barrier theorem, but it's not a counterexample to the limited one. Okay, so we are coming to the end, which is good, because I was a little bit worried about running on. So back to Hume's law. Step one is to establish the taxonomy. Which of the sentences in the deontic modal logic are going to count as normative and which are descriptive? We are going to precisify this idea from the beginning of the talk, that normative sentences are the ones whose truth value is breakable with changes in the normative standards. What does changing the normative standards look like in models? It looks like changing which non-empty subset of W is S. Call this S shifting. And here is an intuitive presentation of it. So the model on the left is exactly the same as the model on the right, except for the shaded area. Right? So that represents the S set, the subset of W. In the model on the left, it's W1 and W2. in the model on the right is W2 and W4. Okay, that is S switching, right? Changing which part of the model is in gray. Okay. So which sentences go from true to false, that is get broken by the S shift from left to right, while we lose, it ought to be the case that P, so P was true in all the grayed out areas on the left, but on the right, we've got W4 in the grayed out areas and P is false there. It's permissible that R, that goes false. And then the disjunction, Q or ought P, and the conditional if P, then PR, they both go false as well. So conditionals and disjunctions get classed as normative. So then we say a sentence is normative if it is S shift breakable. That gives us these things as normative sentences. Some things that are non-normative are P, box P, diamond P, or so logical truths, unsatisfiable sentences, they're all non-normative. And then we get the DML limited barrier theorem. If gamma is not F shift breakable, that is if it's descriptive, and phi is F shift breakable, this is normative, then gamma doesn't entail phi, unless for all models M of gamma, every model N such that N is an S shift of M is such that Vn of phi is 1. Okay, proof goes as before, but let me just finish up by looking at what happens to Merverde's counterexample based on ought implies can. So there's the counterexample. If it's not possible that P, then it's not the case that you ought to P. Not possible P is not F shift breakable, so it counts as descriptive on our taxonomy. Not ought P is F shift breakable, and so it's normative, but the argument meets the theorem's unless clause. In models of not possibly P, right, not P is true at every model, and so there are no S shifts that can make not ought P false. Okay, so is there an ought implies can counterexample to Hume's law? Answer, not if you formulate it right. And that's it, muchas gracias.